There seems to be no intelligent life down here. Get me home. Welcome back to Element 14 Presents. I'm Clement. Does it smell a bit like sci-fi in here? Anyway, I always wanted to have a sci-fi prop from Star Trek, but from the Lost Era. Basically the thing in between the communicator they had in hand and the one that they just had in their badge. So there must be some version in between. Anyway, I want to build that, and let's make it a functional one. So online I've seen a few attempts at building like a functional communicator badge, but they're pretty much all just a Bluetooth device that connects to a phone. The device in the movies and the series is a subspace communicator, meaning it does all the RF stuff on its own and it communicates out from the planet to a starship and back. Thing is, I don't have a starship and subspace communication is not a thing yet, but what is a thing yet is cell phones. So I'm basically, inside my badge, I'm building a fully functional cell phone so it can receive calls on its own, and you don't have to have a phone in your pocket. So this is the actual phone. So it's an actual standalone device. Okay, let's get cracking at collecting the right parts for this project. The core of my project is a SIM800 module. This is a very popular little device that can be had for not so much money. This basically is what makes a cell phone a cell phone. So this communicates with a cell phone tower, allows you to accept or send SMS and phone calls and even data transmission. But caveat with this is a 2G module. And in a lot of places, 2G has already been phased out. Where I live, it's still active as a fallback because we got rid of 3G and use these frequencies now for 5G. But in case the 4G networks basically go down, we still have the 2G as an emergency way of communication or as a fallback solution in harder to reach places. This is what you get from living in an alpine country. On other places, 2G might already been phased out, so you would have to look for a different module that can do 4G, for example. These are usually a bit more expensive, just so you are aware. Because I know some of you may use this project as a basis for your communications projects, I'm including an ESP32-S2, a 32-S3, because it already has Wi-Fi and Bluetooth on board. So in case you want to build a thing that has more than just a cell phone communication, then you can easily do that by basically copying this project and changing the code. So you have an easier start. Also, this provides a lot of storage space in case you want to have data transmission and stuff. But I'm going strictly for phone communications now, just to keep it simple. And I want to push this into a form factor that resembles a thing that could be the Lost Era communicator badge. So it has to be as small as possible, but still there is enough room in there to actually fit real-world 20-something components. Of course, we also need speakers, power supplies, microphones, all that stuff. So best thing is we look at it in KiCad to see how they all fit together first. Welcome to KiCad. This is basically the whole project. The big thing here, that's our main MCU, but the thing that makes everything go is actually this thing here, the SIM800 module. So let's start with the actual MCU. We have an ESP32-S3. That's mainly just because I wanted to give you the opportunity to, if you're fancy with code, that you can add Bluetooth, Wi-Fi functionality, data transmission, whatever you want. It's already here. All you have to do is basically flash the software for it. But you could do this with the smallest microcontroller you could think of. Like an 80-tiny with just 8 pins is completely sufficient to interact with one of these modules. So what they have, basically they have a direct connection for a microphone and a speaker. You could also put amplifiers in between here if you want, if that's needed. Keep in mind that it's really important to have the right power source for this. So there can be voltage sparks. There is a tantalum cap in the module itself, but that might not be enough depending on the batteries that you have. Capacitors are really good at providing high amounts of current for a very short time, and that's exactly what we need here, so we have to add a few capacitors to that to make sure it works. For the power side, we are doing it a little bit different here. I have a LiPo pack inside that is already protected. Usually I put protection in my circuit. In this case, I have to save the space, and the LiPo already has protection on there, and if I basically double protect it, usually that's completely fine, but in this case this will limit the current output, and that could yield to a brownout on the module during the connection spikes where it just demands more current. So to be sure, protect the module, and here is my charging circuitry. This resistor sets how fast you can charge it. That is dependent on how big your capacity is. And this module provides, or this IC can charge at up to 500 milliamps, and my module is about 1300, I think is the LiPo's capacity, so it's fine to charge it with 500 milliamps. I just try to stay at or below 1C for charging, just to make sure that everything works fine. The LED will tell us if the device is charging or if it has fully charged. And these pins are all connected to the main MCU. Our most important connection is TX-RX, a UART connection, because you interact with these modules with AT commands over UART. You can't just pull a pin high and make it do something. You have to issue these commands in the right order to make it do things. But we have also some direct connections, for example, the reset SIM function, just in case we have to reset the whole thing. For some reason we can't do that in code. We can have wake up and the ring pin. The ring pin is basically, it goes low when an incoming call is there. And wake up allows us to wake up the module when we put it into sleep, which we can do over an AT command. So I've put in all the provisions for you to expand on the project, to make this sleep during normal times and then wake up when there's a call received, so you have a very long battery life. That's the way old cell phones did it. They slept the whole time. So just for your service. We have a modern USB-C port on here, but this is one that only supports USB 2.0. There's no point in supporting anything bigger because the microcontroller also only speaks 2.0. This is used to program the microcontroller, and it's also used to communicate with the microcontroller and to charge the whole thing. And also, if we put it in code, then we can talk to the module, the SIM module, directly from this USB-C port. So basically all the messages will get passed through. So if we type in an AT command here, it will get passed through to the actual SIM. So we can debug and test new features or just manually use it, basically. Could be quite handy. The rest is just some power regulation, because the module runs at 3.3 volts. And this module here has very specific power requirements. It works at something between 3.6, I think, to 4.4 volts, which is like right in the ballpark of a LiPo cell, which is like 3.7 nominal voltage, and if it's fully charged, it's 4.2. So we are powering this current directly from the battery. That's why it's called VSys BAT, VBAT over here, and that directly connects to this switch and then to the battery. So only this microcontroller gets regulated voltage and this one doesn't, basically. So how do they interact then via UART? Well, if you would have a 5-volt microcontroller and you would power this thing, then nothing would work. But a 3.3 volt powered microcontroller, and this module is just at this verge of overlap in communication, so that they can talk to each other without burning each other out. But it's like on the limit. Usually you would put a voltage shifter in between. So if you're trying to build something like more production ready out of this, then put a level shifter in between just to be safe. And that's the whole schematic. Shifting over to the actual board layout, we try to condense this as small as possible. and we use both sides for this. So if you can see, here is the actual MCU module. Here's the USB-C port. This is all the charging stuff. Battery connects here. Power regulation is over here. That's the switch. And here we have space for the SIM module that goes on the back. And on the back side, there's also the battery. So basically every height of components that we have to accommodate anyway, we try to combine with another set of components, so the overall thickness is as slim as possible. And I think for this is it's about 8 to 10 millimeters, depends on how you mount the speaker. I decided to let the speaker poke out a bit so I don't have interference with these connectors here. But you could, I think 8 millimeters is doable if you squish everything completely together with a quite a substantial LiPo cell. So if you have like a smaller one that still provides enough power, you could go down to 6 millimeters or so. Should be doable. Now that we have a thing that holds all the components together, we now need a thing that holds these components in its shape, basically. So we need a case. I use FreeCAD, and I just export a step file from KiCad and build my case around that. And this time I'm not just simply 3D printing it. I mean, I'm 3D printing it, but it's not simple. I'm using conductive filament for the case, so it doesn't matter where I touch it, it will always accept the call or hang up. So it's basically a one-button solution without a button, and we can explore the touch interface of the ESP32. So we now know that the SIM800 module is connected via UART to the ESP32-S3, and that one also has a UART connection to the outside over the USB port, so we can still talk to it and have debug messages and know what's exactly going on in a thing that has no display and no other means of communication to the outside apart the cell module. So we now have to figure out how to touch stuff and everything works. Let's check out the Arduino code. Welcome to the code. We programmed this all in Arduino. First, of course, we have to define some things. The only one important for interaction is the touch pin. We use another touch pin that I've broken out basically just as a source for ground. We just pull that low and that's it. We have to define a few functions, and the first thing that we have to make sure on every boot is that we initialize the SIM800 module, and then we are sure that it's connected before we do anything else. So we have this test routine that goes through all the connections and makes sure that everything works, which is called in the setup. There's the setup function. This is also done during setup. So this basically does things like check if the module is connected. Is the pin inserted? Does it know its own pin? Set the volume, set the ringtone. By the way, you can set 20 different ringtones. In here I just left it at ringtone 0. But in between these, we have something called update serial. That's not a normal Arduino function. That's a thing specifically for this project. Just have to find it here. And this basically is a pass-through. So what it does is basically, if there is something talking on the USB, serial in this case is the USB port, serial 1 is the UART port that connects from the microcontroller to the SIM800. So if there is something available on the USB port, I typed something in, like an AT command for example, then it will just forward that to the other port. And if there is something written on the other end, then it will just forward that to the USB port, which means I can talk to the SIM module directly from the USB port, even though they're not directly connected. So the MCU basically just acts as a bridge, which allows me to debug my code and to manually use that module basically as a standalone thing, if you want. Very simple things to pick up and hang up a call. It's just a simple serial command. ATA picks up a call, ATH ends a call. In between, we always call update serial, so we output all these messages, like the OK for having successfully received the command and then executed it, will also be transferred, and we can see that this command has actually been correctly asserted. For the setup, we've basically done everything important. If you are using two serial ports on ESP32, then you have to define them correctly. Serial is usually, if you set that up in the Arduino IDE with CDC on boot, that usually means that this is the USB port. Serial 1 is a freely defined port, and you have to specifically tell it which one it is. The module talks at 9600 baud. This is the communication mode that it uses, and these are the pins that I used in my sketch, which are also the native UART pins on ESP32-S3. But if you're using a different microcontroller, these will be different. Keep that in mind. So you have to set them up fully, not just like this, like you usually do. For some Arduino variants, serial 1 is like predefined. You just start it like that, and it will just work on that specific pins. That's not the case for this module. Yeah, of course we have to read our touch pin to know if we have actually touched the module. And that's pretty much it. The rest is just is basically just touch detection. If it goes over a certain value, then we detect that as an active touch. If it's below that, we just say it's a fluke. It's just to debounce, basically. So this is like touch debounce in its most crude form. So you can see the code is quite compact. There's not much to it. The only thing that you really need to worry about is doing the right AT commands and always checking with a way to debug it if they are received correctly and if they are executed correctly, which a module will tell you by writing OK. If it's not, it will write error. Quite handy. The touch interface was a little bit too twitchy for my taste because the whole case is now conductive, and once it touches myself and then I touch with the finger again, this is basically an unpredictable situation where every time I move the value could change and trigger it without me wanting to trigger it. So I have to insulate the actual conductive pieces from the rest of the case. Also, I encountered an error state when you pull the touchpad directly to ground without any resistor in there. In some cases it gets stuck at that value. So I'm adding a few bodges to the design and I'm reprinting the case. This time I'm using PETG and I'm only printing the inserts that are recessed in here with the logo of nondescript origin in conductive PLA. So only if I touch that logo or the actual touch pin, then this will activate. To make it all work as intended, I had to do a few changes. I added a 1 mega ohm resistor in between my touchpad and ground. Since I didn't have like a direct ground pad on there, I used the other touchpad that I've broken out and just pulled that to ground in software. That worked pretty good. Also, the case changes, and for power, once the module has booted up, it will try to connect to a cell tower. This can take up to 2 amps of power for a short burst, and some batteries might not be able to deliver that. There is a tantalum capacitor on the SIM800 breakout board that I got that should be able to provide the necessary voltage and power during these short bursts, but it seems it's just a little bit, maybe the capacitor is too old or it's just a little bit not enough. So I add a supercap with 0.1 farad, yes, not microfarad, farad. In between I got one with a very flat footprint basically, so it still fits into the case. Added that and now it works a treat. Okay, here's our completed project. Now only the black parts are conductive, and of course this little piece of wire that I put out of here. You could melt this inside the conductive pieces to make it one, and then basically everywhere you touch you have the contact. I didn't do that because I want to be able to still remove it from the enclosure for debugging. So, but now everything we've built up is in here. Here's the speaker, here's the microphone, here's the USB-C port, and this is a little badge holder that I got from a trade show. Kept that one, and now I can just clip it on my uniform, basically. And now we can just turn it on. The power switch is on the top. Just need a little tool to activate it, because in reality you would just keep this going all the time, right? And just let it sleep when it's not really in use. And now I can take out my phone and call it, if nothing goes completely wrong. Oh god, I think it's smelling a bit. It's actually ringing, and now I can pick up the call. Hello? Hello, hello. Oh yeah, and now I can hang up. Yep, that worked. Don't let me forget to blur out the number, or you can call me in my sleep. Yeah, that's my working communicator badge. Now I can call it, take a call, and basically be ready for new adventures out in space. Hello? Still smells in here. Anyway, if you are interested in the project files and the code and whatever, you can download all that for free on the Element 14 community. You can also go there to chat with me and all the other hosts, and maybe you have an idea for a project that we can build on the show. Let me know. I gotta go. There's another project waiting for me.